The operating principle of this wave power station is as simple as it is ingenious. An enclosed chamber has an opening below sea level which allows water to flow into the chamber and back. The water level within the chamber rises and falls within the rhythm of the waves. Air is forced forward and backward through the turbine connected to an upper opening in the chamber. As air is compressed and decompressed, it has sufficient power to drive the Wells turbine. It is a feature of the Wells turbine named after its inventor that it is driven in the same direction by both forward and reverse airflow through the turbine. Even relatively low wave motions can generate enough airflow to keep the turbine moving and to generate energy. This is how easily energy can be generated with a wave power station, day and night all year long as there are waves. Our power generating technology concepts recreate nature's hurricane and storm conditions. We take advantage of the thermokinetic thermal variations to convert these natural conditions to generate a useful energy source. KITHD, Thermofluidics Energy Conversion Concept, first thermokinetically excited, heat up, then alternately cooled, high pressure, pre-charged compound gases and ionized magneto-responsive fluids, generating forces, converting to straight rotary motion. Comparisons layout of diesel engine generating plant, gas turbine generating plant, and kinematically independent thermohydrodynamic turbo-compound generating plant. Realities of reliability, the modern thermal kinematic power conversion engines. The engineering community should congratulate Caterpillar engineers for developing connecting rods, which is a possible tie to the knots. This is a great achievement, but for what? A diagram illustrating the principles of external thermal supply engines. John Erickson, Sterling ETC. When R. Diesel patented his P-const cycle, diesel fuel wasn't in existence. Modern compression ignition, so-called diesel engines, do not operate on the patented cycle at all. Rudolf Diesel P-const slow combustion cycle. Modern compression ignition engines operate at thermodynamic PV-const cycle patented by engineers from Russia and France. Trinkler Sabbath PV-const combined cycle. So-called free piston engines, some engine configurations defined as the free pistons. In fact, those free pistons are not so free at all. A few years ago, William Beale of SunPower Inc. came up with an ingenious configuration combining a 4-cylinder free piston alpha engine with so-called gas turbine output, only it is not clear on how this free piston configuration synchronizing system worked and where, because there are about 36 plus valves missing. The engine below is an engine originally developed by Charles Gaggen. Once again, engineers have turned to turbines to convert power from reciprocal to rotary, using the gas energy generated by the piston engine. German engineer Peter Fett prototype of the 2x double-acting Stirling engine, the so-called WW engine, reciprocal thermal motion of the gas-liquid column still converted to rotary motion by pistons, rods, complicated, non-efficient Scotch yoke mechanism. Kinetically independent thermohydrodynamic theoretical thermodynamic PV and TS diagrams. Complex. Isochoric, isobaric, polytropic, PV and varia dynamic regenerative cycle contains 6 governed variable thermodynamic phases. Phase 1 to 2. Variable ratio isobaric compression. Phase 2 to 3. Variable polytropic compression. Phase 3 to 4. Variable ratio isochoric thermal accumulation. Phase 4 to 5. Variable ratio isobaric expansion. Phase 5 to 6. Variable polytropic expansion. Phase 6 to 1. Variable ratio isochoric thermal rejection. Oxidizers independent block diagram. Digital electrodynamic governor. Oxidizers independent thermal generator. Auxiliary mechanisms. Cooling exchangers. MHD amplifier. Kinematically independent THD turbo compound generator. MHD amplifier. Controls and instruments. DC rectifier. Permanent magnet generator motor. DC AC inverter AC power out. Battery banks. Oxidizers, Reliant block diagram, Digital electrodynamic governor, Oxidizers, Reliant thermal generator, Auxiliary mechanisms, Cooling exchangers, MHD amplifier, Kinematically independent THD turbo compound generator, MHD amplifier, Controls and instruments, DC rectifier, Permanent magnet generator motor, DC AC inverter, AC power out, Battery banks, Oxidizers, Reliant fuel, Combustion oxidizers, KI-HMD turbo compound generator fluids flow diagram, Quantum nucleonic reactor, KI-THD thermal energy generator, Primary thermal absorbers second set 242, Primary thermal absorbers first set 241, Integrated active dynamic regenerators and active main cooling exchangers, hot ionic liquid in, main reciprocal gas thermal exchangers, accumulated thermal energy ionic liquid out, main reciprocal gas thermal exchangers, EMD thermal actuators, ceramic matrix, EMD thermal actuators, EMD cooling actuators, cooling ionic liquid out, main reciprocal gas cooling exchangers, cooling ionic liquid in, main reciprocal gas cooling exchangers, displacement power generating module 222 involutes, inner thermal exchangers, thermal compound gas, electromagneto hydrodynamic actuator, thermal ionic liquid, kinematic bidirectional turbine, thermal ionic liquid, electromagneto hydrodynamic actuator, inner thermal exchangers, primary cooling exchanger, cooling linear induction pumps, compression and power generating module 450 involutes, inner cooling exchangers, cooled compound gas, electromagneto hydrodynamic actuator, kinematic bidirectional turbine, ionic liquid, electromagneto hydrodynamic actuator, cooled compound gas, inner cooling exchangers, KI-THD power conversion module, impulse turbine geometry and velocity vectors, velocity triangles, bidirectional impulse turbine wheel, bidirectional Wells turbine wheel, bidirectional Wells variable pitch turbine wheel. Therefore, we can still knit knots from connecting rods as displayed, or we can build real free liquid piston engines.